presentation and for giving me the opportunity to present the company where I work. So this presentation will be split into two parts. So I will first introduce Acciai Bertolisa FAU, steelmaking company. And whereas the last part of the presentation will be dedicated to the presentation of our R&D division, ACM, as well with, let's say, the main activities they are in charge for. So let's start by saying that Acciai Bertolisa FAU is a steelmaking division of Danieli Group. So our mother company, Danieli, is, let's say, one of the leaders worldwide in designing and manufacturing steelmaking plants. So any kind of equipment which is concerning with the manufacturing, with the production of steel, not only steel. Whereas ABS is the steelmaking division, which means that we use mainly Danieli's technology for the production of steel. So we produce mainly, let's say, special steel grades, and we only produce long products. So ABS is quite a, well, young company. It was born in 1988. But it was born because of the merging of two pre-existing old steel mills, which were called Officine Bertoli and Acciai FAU. In 1988, they merged. Danieli entered the group, and since that moment, let's say that the company started to evolve thanks to the installation of different kind of new equipment for the production and processing of steel. We are a company, we are investing, I would say, quite a significant amount of money in the installation, continuous installation of new equipment. For instance, in the last 5 years, over 600 million euro were invested mainly to, let's say, increase our rolling capability and also, let's say, the quality of our products, and also to enlarge the size range of our products. Acciai Bertolisa FAU is located in Udine, it's a small town in the northeast of Italy, let's say about 100 kilometers far from Venice, towards the border with Slovenia on one side, on the eastern side, and with Austria on the northern side. This is where the main, let's say, productive site is placed. There is also a second smaller productive site, which is located in Croatia, in Sisak, not far from Zagreb. As I said, our R&D division, ACM, which stands for ABS Centre Metallurgie, is based in Metz, in France. And we have, let's say, some commercial sales offices spread in Europe, apart from Italy, in Spain, Germany, and Sweden, where also our, let's say, main European customers are present. We are, let's say, exporting steel in many different countries worldwide. Let's say that about 50% of our output is delivered, is sold to Italian customers, whereas the remaining 50% is mainly delivered in Europe, and about 10% of our output is exported out of a European community. We are producing many different steel grades, over 1,000 different steel grades, which are mainly used for mechanical engineering purpose. But our, let's say, very important sectors are also the automotive sector, as well as oil and gas and power generation, and many other, let's say, smaller applications. An overview on the most typical final application of our rolled products. If we consider the automotive sector, which is including also trucks, agricultural vehicles, earth-moving machines, most of our bars are either forged or directly machined to get a wide range of parts used for the hangings, for the transmissions or the chassis. We talk about both long pieces and hollow parts, such as gears, for instance. The oil and gas market is important for either the forging of valves, nozzles, but also for direct machining of many different parts which are used in the drilling equipment. A very important sector, especially for the very large products belonging to our size range, are the blooms, which are often directly sold to our customers for the forging of planetary gears, shafts, flanges for the eolic towers, as you may see in this drawing, but even let's say fasteners, which are used for eolic towers as well. So really, as you may see, a very wide range of products is one of the most let's say interesting features of our plant. Another let's say important application for our products is what we call a railway sector. Our bars are used for forging and machining of wheels and axle for trains, including also high-speed trains, as well as for some suspension parts and for some parts which are used in the braking system of trains. I would say that if we have to summarize what our key points are for our company, I would say that sustainability, innovation, and care for people are the most three important topics. When we speak about sustainability, we of course mean sustainability not only from an economic side, but also from environmental and social side. If we speak about innovation, we will later see what we mean by saying, let's say, innovation in the production of long products. And people, of course, is a key driver for supporting innovation and sustainability. So if we move to the description of our production process, let's say that ABS is a steel mill, which is starting from scrap. Therefore, the scrap is collected into scrapyard, and then it is charged into one of our electric arc furnaces, where it is melted. Once it is, let's say, melted and tapped from the electric arc furnace, we have several ladle furnaces station and vacuum degassing tank, where we carry out refining process, and for most of the grades, the degassing process as well, as it is a very important step of the process for guaranteeing high level of quality to the grades that we produce. Once the steel making process is completed, the solidification of the steel can be carried out by choosing either continuous casting machines or ingot casting. So we can solidify the steel either by means of continuous casting machine or in a more traditional way into ingots. Once the ingots on one side or the continuous cast blooms on the other side are produced, we stock them, then we reheat them inside either working metal furnace or pit furnaces, in the case of ingots, and we use one of our rolling lines. There are 3 rolling lines in ABS in order to transform the semi-finished products into rolled bars, which then can be sold either in straight condition or in the shape of wire rod. Once we have produced the bars, they can be directly sold in untreated condition to our customer, or we can, let's say, perform different kind of heat treatment processes, most traditional, of course, treatment processes, such as annealing, normalizing, quench and tempering, and deliver the bars in treated condition. As we produce quality steel grades, it's mandatory for our rolled products to be inspected in order to ensure, let's say, quality for the surface and also internal quality. Here you can see a picture from the top of our main productive site, which is the site of Udine, so the Italian site. And here you can also see, let's say, the disposition of the different plants. Basically, we start by collecting the scrap into a covered scrap yard. And then we have the two melting lines. Each melting line is formed by an electrical furnace, a ladle furnace, and a vacuum degassing treatment station. We have very recently started a new LF and VD station in order, let's say, to increase our capability for these processes. Another electrical furnace in line with ladle furnace and vacuum degassing treatment tank is placed in the mill that we have in Sisak in Croatia. So in ABS Udine, we have 3 continuous casting machines. The machines are different with respect to the casting size. We call them in a very easy way, CC1, CC2, and CC3. The most interesting continuous casting machine is the CC3, which is also called Hercules because of its size. I will later show some, let's say, details about this almost unique machine. And here you can see also in the middle the ingot casting area where we can solidify the steel into ingots. Once the steel is solidified in a, would say, perpendicular direction with respect to the direction of the steel mill, we have the different rolling lines. We call them with an Italian name, which is Luna and Marte. Luna is the rolling mill where we produce the smallest size range of straight bars, whereas Marte is our jumbo mill where we produce sizes which are the upper side of our size range. Here you can also see the QWR. QWR stands for quality wire rod. This is a brand new wire rod mill which was started almost 1 year ago. So really a brand new plant, which is allowing us to produce wire rod in a size range from 5 up to 25 millimeters of diameter. I will later show some details also about the most recent plant installed in our company. On the left side of this picture, you can see what we call quali steel, which represents the bright bar division, so the division where we perform finishing of our bars. So I mean peeling and reeling, grinding processes in order to provide the material with a better level of surface quality in terms of tolerance. And we also have, as I said, different heat treatment facilities for carrying out either annealing or normalizing or quench and tempering. So we can use either continuous furnaces, batch furnaces, induction furnaces, gas furnaces. So we have quite a wide range of possibilities to perform heat treatment processes. As I said, we produce more than 1,000 of grades. Our yearly output, our yearly capacity is about 1.4 million tons. And therefore, we are considered quite a big mill for the production of long products, at least in Italy, of course. This is our range. I would say this is one of the strongest points of ABS because basically we start by rolling 5 millimeters wire rod, and we can deliver up to forged bars with a diameter of 1 meter. In between, we are really covering almost any possible product in either round or square shape. We have a wide range of continuous cast blooms, most of them in round section, starting from 200 millimeter up to the biggest size, the jumbo size of 850 millimeter round. And this wide range of conti cast blooms is allowing us to offer to the market, to the customers, a wide range of hot rolled products as well, starting from 29 up to 500 millimeters of diameter for round bars. Then, of course, we can, if needed, either peel or turn or perform some kind of finishing to enlarge even more this range of products. I will now I will not describe step by step all the facilities, all the productive facilities we have in ABS. I will just focus on what is more, let's say, interesting and more unique among the machines that are installed in ABS. One of it is for sure what we call continuous casting number 3, because this is one of the largest continuous casting machine in the world for the production of blooms. It can cast blooms starting from 500, which means half a meter, up to 850 millimeter. It's a curved continuous casting machine with a radius of 18 meters, so really big continuous casting machine. It has 2 electromagnetic stirrer per strand, and it is allowing us, or it has allowed to ABS to replace a significant amount of ingots as a starting product to roll very big rolled bars, but also as a starting product to be directly sold to our customers for hot forging applications, such as ring rolling application, open die forging of really very large products. So this is really quite a unique plan. There are not that many machines that are bigger than this machine. For sure, in Europe, it is still the biggest one. Out of Europe, okay, I think that in China you can find something bigger, but it remains one of the biggest continuous casting machine. And what is interesting is that we can cast almost any kind of the grades that are produced in ABS. So we could cast high carbon grades, we could cast high chromium grades. So we could adapt this machine to cast also, let's say, critical grades from the side of solidification with good performances in terms of core soundness. Another, let's say, unique plant, unique equipment, sorry, that we have installed in ABS is what we call the rotoforge. This is a rolling stand, as you can see in this picture. What is particular of this stand is that this is the largest stand in the world for the rolling of long products. The maximum diameter of the cylinder of the roll that is used is 1.8 meters. And we can roll bars up to 500 millimeters of diameter with very good performances in terms of internal soundness. This stand, this rolling stand, is capable to ensure a good level of internal soundness, which makes these products not so far, not so different from typical forged products that are obtained by means of forging instead of rolling process. Thanks to the fact that a high reduction ratio, but also a high squeezing capacity, so capacity to deform the material up to the core, can be applied to the bars under rolling. Bars which can be rolled from either huge, big Conti cast bloom or by ingots. Let's say the newest plant, which was installed almost 1 year ago, or just a little bit more than 1 year ago in ABS, is so we are completely on the opposite side of our size range. I've just showed you, I've just talked about the rolling of big bars. Now I'm moving to the rolling of wire rod. This is a wire rod mill. It's a plant with a very big capacity because the maximum capacity is almost 500,000 of tons per year of special steel wire rod. The size range is the typical size range, 5 to 25 millimeters of diameter, therefore capable to cover most of the application, most of the products which are, let's say, obtained by wire. It's a brand new plant with a very high level of automation. In fact, we call it a quality wire rod 4.0 because let's say that Daniele has tried to develop the approach, zero man on the floor approach, as well as the highest automation level for this kind of plants. The full process is controlled remote way. We have tried also, let's say, to develop in terms of reheating process, low scale and energy saving reheating processes. We have tried to set up the highest level of control of the size range during rolling. We have tried to, let's say, implement, and we are developing the process in order to control temperature and cooling during the rolling mill to ensure thermomechanical conditions, for instance, thermomechanical rolling on products which are, let's say, requiring this kind of treatment, or products where the performances can be improved by applying the thermomechanical rolling process. We have a long cooling conveyor where we can manage the type of cooling grade by grade. If we need faster cooling, we have fans. If we need slower cooling, we have hoods. And we really can control the mechanical properties in a direct way of a wide range of grades. Finally, we can store the coil, especially the most critical products, inside in a fully automated warehouse where, let's say, man is not present, so we can, let's say, track the place where the material is stocked and then call it when we need to ship the material to the customers. We are trying to develop, so we have started by what were the most common grades for ABS, and we are now trying to develop the production of a wide range of segments. So I have reported just a few examples on this slide, such as high carbon, low carbon, CHQ grades, bearing grades, welding grades, spring steel, and so on. So we are really trying to develop most of the grades which are interesting for the application of wire rod. So this is really a very short introduction about and a very short description about ABS. Let's now move, let's say, to what our R&D division is. As I said at the beginning of the presentation, our R&D lab is located in Metz, in France. It is called ABS Centre Metallurgie. There are 18 people working in Metz with different kind of graduation and skills. But all of them are oriented towards, let's say, support, towards giving support for either the development of our processes, therefore to improve the performances of our products by controlling and improving our processes, and towards, let's say, the development of new products, new grades, or the modification of existing grades, trying to follow our customer needs in terms of higher reduction, for instance, of CO2, hydrogen sensitivity, better performance in terms of mechanical properties, fatigue, and so on. ACM is mainly working for ABS, but these guys can also offer, let's say, services externally, thanks also to the fact that the laboratory of Metz is qualified ISO 17025 for, let's say, some of the most common and typical characterization tests which can be carried out on steel. But I really want to spend this a few minutes just to present some of the activities that ACM is following. For, as I said, ACM is providing assistance and support for either industrialization of development of the new grades, thanks to the fact that we can, let's say, perform a deeper characterization than the standard one as far as the macro cleanliness and micro cleanliness of steel concern. We have an ultrasonic immersion tank for UT test. We have, let's say, electron scanning microscope, automatic inclusion, indication, and classification. We can perform plastodilatometer tests in order, let's say, to provide further informations about the grades that we are studying. We can, let's say, we are using several predictive modeling and several tools in order to try to model our processes, and we are also, let's say, committed to try to develop new solutions to be offered to our customers, which are mainly following two directions. We are trying, of course, to make our products more sustainable, for instance, by developing grades that are not needing heat treatment processes. We are also trying to provide higher performances to our steel products in order to let our customers achieve downsizing of parts, and therefore lighter final parts, and therefore reduction of emissions of CO2. These are, I would say, the most important directions we are trying to give to the development of our products. And if we speak about support for, let's say, development of our processes, which of course aim also to provide better performances to our products, we are developing what we call hybrid twins project, for instance, about the continuous casting, about our ingot casting processes, about our rolling processes, for instance, try to model reheating processing and rolling processes, aiming to achieve the best core conditions to our rolled bars. And we are developing models also for our second rolling mill in order, for instance, to try to optimize the plastic deformation under rolling, therefore achieving better surface quality and better surface performance to our bars. So that is really a very quick overview about our company. I have finished. I hope to be on time, not too long, but thank you for your time. And if there is any kind of question, but if we are not too late, because I don't want to keep time to the lesson, I'm here.
It's up to Harry to decide. As for me, as you would prefer, Harry. I don't know if you have any other issues that you prefer to start.
No, I think we'll take questions. So I have one question. In the new wire rod mill, you explained that you have hoods to slow the cooling rate down and fans if you want to accelerate the cooling rate. So what sort of product requires you to slow the cooling rate down?
Okay, so let's say that there are grades which needs to be developed to be delivered with very soft properties, such as CSQ quality. So this is material which are then drawn and cold forged. So anybody who is doing the cold forging is of course needing soft material. There are some grades which are, let's say, more critical, and we need to go through annealing processes out of line. But there are many other grades, such as boron grades, typical boron grades for CHQ quality, where we need to slow down as much as possible in order to guarantee a maximum hardness and a maximum tensile strength to be cold forged directly without the need for any annealing treatment before.
Okay, so the cold forging grades are not related. Cool them.
Sorry?
The cold forging grades, which are cooled slowly,
yes.
Are not in a polytic condition at room temperature?
No.
Okay.
No. We need to do this kind of, for instance, we have to ensure 600 megapascal, 620 megapascal maximum. When we start to have medium carbon grades with boron, with some chromium and manganese inside, we need to slow down the cooling. Otherwise, they result too hard to be directly cold forged. And what our customers are trying to do, they are trying to avoid annealing and also globular annealing for some grades. Other grades, of course, this is not possible. But I would say that all CHQ grades are requiring a maximum hardness, and in many cases, this maximum hardness can be guaranteed without the need for any annealing process, just by working with the hoods and slowing down the cooling process.
Thank you.
You're welcome.
Thank you so much, Francesca. So Harry, when you would like, if there are not any other questions, then maybe they can be done when you have finished your lecture. I think we would go on, and I will leave the screen as for you. So thank you so much, Francesca, again.
Welcome. Thank you to you.
Okay, so my talk today is about twinning-induced plasticity steels, but I will also relate to another problem, which involves transformation-induced plasticity. Now, the twinning that I'm talking about is mechanical twinning. In other words, twinning associated with a physical deformation as opposed to annealing twins. And what do we mean by a twin? Well, supposing that I have a lattice like this, and I shear it homogeneously, then this part now reflects about the twin plane into the original structure. So this plane, this is a particular kind of twin that is quite common in the sort of steels that I'm going to talk about, where you can generate the twin lattice by a reflection of the parent lattice across the twinning plane. And of course, there's a physical deformation, which is a pure shear on the twin plane. So that is mechanical twinning. And in the case of austenite, the twinning system, that means the plane on which the twinning happens, is the close-backed plane, the one-on-one type plane, and the direction in which the twinning happens, the twinning shear is directed. Okay, so I'll repeat that. So the twinning system in austenite consists of a twin plane, which is the close-back plane of the austenite, and a twinning direction within that plane, which is of the type 112. So I will illustrate that later, but that is the twinning direction, which is the 11-bar-2 in this case, and the twin plane is the plane which remains unaffected by the twinning deformation, which is the 1-on-1 plane of the austenite. And of course, we know that the 1-on-1 plane is close-backed, which means that the atoms touch along all three directions, and there's a high packing density inside that plane. So the close-back planes are stacked above each other in the FCC structure of austenite in a sequence A, B, C, A, B, C. Now, what do we mean by that? Well, if in this particular plane, the atoms are located at positions A, then there is a sort of a dip in between these three atoms, which is a position B, where the atoms in the plane above can lie, or in a position C. If I translate just from A to A, that doesn't change the crystal structure, okay? So that is simply like slip happening along the 110 type directions. So that's the 110 type direction. A translation through that vector doesn't change the crystal structure. However, this direction A by 2, 110, where A is our lattice parameter, can be split into two 112 type vectors here, A by 6, 211, and A by 6, 12 bar 1. And if I translate the layer above this layer from this position, which is a C position, to a B position, then I actually change the crystal structure. I've introduced effectively a fault in the lattice. And if I carry out this translation on every single 111 plane, then the result is a twin, a mechanical twin in the austenite. So the displacement is A by 6, 211 here, Okay, and the distance over which that displacement happens normal to the closed back plane is the spacing of the 1-1-1 planes, which is A upon √3. So the twinning shear is simply the displacement divided by the height over which it happens, which is 1 over square root of 2, or 0.7071. So that is a very large shear deformation. If you recall my lectures on martensite and bainite and so on, the shear was only about 0.26. This is 0.7071, or 1 upon √2 to be exact. So twinning involves very large deformation, and that's why mechanical twins will always form in the form of very thin plates in order to minimize the strain energy. So this plane here is our closed back plane, and I'm stacking them in a sequence A, B, C, A, B, C, illustrated over here. So this represents our face-centered cubic crystal structure of austenite. And this is a repetition of that stacking sequence, A, B, C, A, B. And now I'm going to displace one of the, I'm going to displace one half of that crystal relative to the other by A by 6, 1, 1, 2, and that results in this. So we have A, B, C, B, C, and then conduct another displacement on an adjacent closed back plane, and that results in A, B, C, B, A. So notice that about this twin plane C, I have reflected the crystal structure. So B reflects to B, A reflects to A. So this is our mechanical twin, and its lattice is a reflection about the twin plane of the parent structure. Okay, trip steels. So this is a very classic paper. The reference to this will appear later in the presentation, showing austenite which deforms by mechanical twinning and dislocation sleeve. So this was a sample which was originally flat, and after deformation you can see all the surface relief here caused by mechanical twinning in the different austenite grains. And in a transmission electron micrograph, these twins are extremely thin, okay, because of the very large shear deformation. And of course, you also have an increase in dislocation density, because it's not just twinning alone, but also dislocation slip that occurs at the sort of deformations we subject twinning-induced plasticity steels to. I'll tell you the composition later, but these are quite remarkable materials, because look, this is a stress-strain curve. Yielding, the yield strength in this particular case is really quite small. It's about 300 megapascals. But you can continue the deformation until the strength exceeds 1.2 gigapascals and maintain an elongation of something like 60%. Okay, so this is quite a remarkable combination of properties, an elongation of 60% and a strength of 1.2 gigapascals. But it starts off at a low yield strength, and then it looks like there is a steady work hardening rate as you continue deformation. So what is the reason we don't get an early plastic instability? You know, just like in normal steels, you don't get to 60% elongation at this level of strength. Well, what's happening is something known as a dynamic hole patch effect. In other words, the formation of the mechanical twins effectively reduces the grain size of the austenite. So as the twins form, the effective grain size in the hole patch equation is decreasing during the course of deformation, and that is what gives us the work hardening that prevents an early onset of plastic instability. So we are not transforming this austenite at all into martensite or anything like that. It's just mechanical twinning, refining the effective grain size as deformation proceeds. And the mechanical properties are quite remarkable, apart from the strength and elongation. You know, if you look at the impact energy as a function of temperature, there's virtually no change here as a function of temperature, because you know, if you recall what I said about the ductile brittle transition temperature, the austenite does not have a ductile brittle transition temperature because the flow stress always remains below the cleavage strength. So trip steel's typical composition is 25 manganese, 3 silicon, and 3 aluminium. If you only had the manganese and iron, you would still get it fully austenitic, but it would tend to undergo phase transformation to epsilon martensite as you deform. But the addition of these further elements, there are various reasons for adding these elements, but one reason is that you remain fully austenitic as you deform. Now, because silicon and aluminium have low atomic rates, the overall density is actually reduced quite significantly. So the normal iron has a density of about 7.8 grams per centimeter cube. This is 7.3 grams per centimeter cube, and it's fully austenitic and maintains its properties to cryogenic temperatures. So one application for trip steels with POSCO as considered is the pressure vessels used to carry liquefied gas. Okay, they are usually made from 9% nickel steel, but they have also made them from trip steel. And of course, you know, as you lower the temperature, there's no significant change in toughness. Therefore, there's also no significant change in toughness as you increase the strain rate, so to 10 to the power of 3 per second. Now, everything looked very promising for these trip steels for many years for automotive applications, because, you know, if you have a large elongation and a large strength, then that's a good thing for formability. But when some components were made, they tended to crack spontaneously after a certain period of time. So this is known as static fracture, and it's illustrated here in a cup that has been drawn out by drawn out from trip steel. So this is a 22 manganese 0.6 carbon trip steel, and after an unpredictable amount of time, the cup simply cracks up. Now, the purpose of drawing out a cup is that you also have residual stresses inside that drawn cup. That combined with something else causes this static fracture. But the addition of aluminium gets over the problem. However, when the static fracture problem was highlighted, the automotive industry basically abandoned trip steels because they thought of them as being unreliable. The problem is actually solved, you know, by the addition of aluminium. And there are various ideas on how this stops this mechanism of fracture, which is associated with hydrogen embrittlement. Okay? So this kind of fracture can be accelerated by introducing further hydrogen into the material. So there must be something about aluminium which prevents that hydrogen embrittlement of austenite. And there are various models for this, but one which is really interesting is that the aluminum atom causes a localized expansion around it. So for example, if this is our face-centered cubic unit cell, and these are the heights of the atoms, these are the face-centering atoms, then the distance between the iron atoms and the aluminium atoms is larger than between the iron-iron atoms. So there's more space created in the interstices between the substitutional atoms. And that is where hydrogen gets trapped. So it's a deeper trap for hydrogen than inside the lattice, and therefore you prevent hydrogen embrittlement of TWIP steels. Now, although I said that you know, automotive applications have essentially been abandoned for trip steels. People tried to create crash resistance using trip steels because they can continue to deform to a large degree of deformation. So the kind of objects I'm talking about, on this side we have a composite material, on this side we have a steel. And what you do is you want the material to absorb energy. In the case of the composite, it's by breaking interfaces between the composite components. And in the case of steel, by forming this concatenated structure, which basically absorbs energy by deformation. Now, the problem with trip steel is that its strength only rises gradually, okay? Whereas in this kind of a scenario, you are only putting large strains in localized regions. And therefore, you don't absorb as much energy as you would expect if you had a curve which was flat like this, except near the yield region. So this application doesn't prove to be successful. However, some very clever engineering by the German railway system has provided a new kind of an application for trip steel, where in a crash scenario, the whole of the material would deform uniformly. Now, how did they find this engineering solution? Well, these are the crash energy absorbing devices in a railway tram, railway carriage. And what you do is you have these pipes made out of trip steel, TWIP steel, and during a crash, these pipes get extruded through dies, and therefore the trip steel is uniformly deformed everywhere up to its maximum capacity. And I'll show you a video here of the actual behavior of this during a crash. So basically, you're absorbing energy by extruding the trip steel. And I don't know if you saw, but there was a extrusion of those trip steels through the dies, absorbing energy and stopping that train carriage. I thought this was an incredibly clever mechanical engineering solution to the problem. So trip and TWIP involve transformation or twinning deformations caused by an externally applied stress. And both of them work by increasing the work hardening capacity of the material. And they both lead to, therefore, to greater strength and greater ductility. Now, I want to change the subject a little. Here, in all the examples, both in trip steels and TWIP steels, we are exploiting the phenomena by physically deforming the material using an externally applied stress. Now, is it possible that stresses that are generated when constrained components cool, in other words, residual stresses, they themselves can trigger these effects and therefore cancel out the residual stresses? Okay, I want to show you an example where transformation-induced plasticity is used to stop the accumulation of residual stress as large components which are constrained are locally heated or cooled. So welding is an obvious example because we take two bits of steel and in between we put liquid metal, the liquid solidifies, and these, if your component is large, then these parts don't really want to move as the weld contracts, and therefore you accumulate stress. So that's illustrated over here. Liquid can of course flow, so there is zero stress when this weld pool is liquid. As soon as it solidifies and the temperature drops, it will start contraction, and therefore you will build up a residual stress. And residual stresses can be very bad for the component in several different ways. So if there are any stress concentrations, they induce fatigue failure because the applied stress will be complemented by the residual stress. it also means that the stress that you apply to the component has to be smaller than you would expect from the yield strength of the material used to make the component. So is there any way that we can compensate for this kind of thermal contraction, where after solidification, you basically build up stress simply because these two ends are completely constrained? So if this is a very large assembly, you know, like one of these platforms, or you're welding pipelines, etc., then residual stresses can be extremely important in your design process. Okay, so imagine that we have a sample here, which is an austenitic stainless steel and remains austenitic at all temperatures. So this was a classic experiment done in 1977 by Albury and Jones, where they heated this tensile sample to a high temperature and then physically fixed it and allowed it to contract. And as it contracts, you get an accumulation of stress. It's not, if it was only thermal contraction, this stress would rise rapidly. But at high temperatures, some of the thermal contraction is accommodated by ordinary plastic deformation. Okay, so the rise in stress is lower than you would expect, but nevertheless significant at about 300 megapascals. Now, supposing you do the same experiment with a steel which transforms during the cooling process. Okay, so this is now a bayonitic steel, and once again we get the rise in stress due to thermal contraction. But as soon as we get the onset of phase transformation, that compensates for the thermal contraction, and we get a reduction in stress. However, when the phase transformation is exhausted, that means all the austenite has gone, the stress begins to rise rapidly, okay? And we end up with a large residual stress at room temperature. Okay, so what happens if we lower this transformation temperature? So instead of bainite, if we now produce martensite, once again, the same phenomenon until we get phase transformation, we cancel out the effects of thermal contraction, and because the transformation is exhausted at a lower temperature, we end up with a smaller residual stress. So this gives you an idea on how to design a welding alloy that would leave your component with a zero residual stress at ambient temperature. All you have to do is move this point to somewhere along here. Okay, so cause the phase transformation to happen at a temperature of around 200 degrees centigrade, and all the austenite should be used up by the time you get to ambient temperature, because we don't want retained austenite left. Now, when designing a welding consumable, you can't simply just alter the transformation temperature. You have to look at a very large range of mechanical properties which have to be satisfied. For example, the toughness measured in either of these ways, or the fatigue properties, corrosion properties, etc. So a design problem is never simply a single parameter. And that is where, you know, graphene has gone so badly wrong that they were looking at the strength of a carbon-carbon bond and then claiming all sorts of things. But you can't actually use that at all for structural applications. You have to have a whole bank of properties in order to make something useful. Okay, so how do we do this? We have a lot of experience in designing welding alloys. And this is a commercial alloy. Quite straightforward. All of these contain a very low carbon concentration because we don't want to produce martensite. There's a certain amount of silicon and manganese added for deoxidation, because remember, you're pouring the liquid without any of the normal refining processes that we implement for normal steels. And there's a certain amount of hardenability required to avoid high temperature phases. So this is a commercial electrode which transforms at a high temperature of about 450 degrees centigrade. These are three alloys which transform at low temperatures. And you can see that the nickel concentration here is quite high. Okay. to force the transformation temperature to a lower temperature. Now, the first thing that a steels person will say is that, look, nickel is expensive. But remember that the amount of welding material you use is not very large, right? And furthermore, if you increase the life of the component, then the overall cost is actually reduced. So never just look at the cost of an alloying element. Look at the benefits that it produces, and whether, if you look at the whole life cost, is that reduced? So we designed these three alloys and decided to repeat the Albury and Jones type experiment, but this time also using X-ray diffraction to follow the phase transformations and various other features of the behavior as the material cools. So this is effectively a dilatometer that is attached to a beamline at Grenoble. So there's a high energy X-rays coming out from here. And this is our sample positioned inside the dilatometer. And we can monitor everything that happens, the stress, all the information from the high energy X-rays and so on as the cooling happens. So it's straightforward from X-ray diffraction to calculate how much austenite you get and how much ferritic transformation products you get as the material cools quantitatively. Okay. So I'm going to show you now the Albury and Jones type curves taken using the technique that I've described. So first of all, this is our control electrode, which transforms at a high temperature. And you can see that you're left with a large level of residual stress in the specimen by the time it reaches ambient temperature, because the transformation is exhausted at this point. For all the other alloys, where the transformation temperature is of the order of 200 degrees centigrade or lower, we end up with almost zero stress or even a compressive stress at room temperature. Now, of course, these are tensile specimens, and what you've got to do is prove this for an actual weld metal. And these tensile specimens are roughly 5 millimeters in diameter, because the X-rays can then penetrate the whole of the specimen. Whereas a weld will be a much larger object, which cannot be penetrated by X-rays. So we went to Chalk River in Canada to make measurements of residual stress inside actual welds. And these are the results. This is our control electrode, and you can see that we've got large tensile stresses here in the heat affected zone and so forth. And this is the low. These two are the low temperature transforming welding alloys. And look, we've got minus 600 megapascals of compressive stress here, and similarly minus 600 here. Okay, so this method actually works, and there are many tests now in the literature, going from the work of Ota and so forth, which show that actually the fatigue properties are improved because of this compressive stress system that you develop. Now, supposing that we wanted to design, so these are actually transformed into ferritic transformation products, but supposing we wanted to design a stainless steel and containing a large chromium concentration, okay? So we need a chromium concentration greater than 12 weight%, because that's gives you a reliable, coherent and adherent chromium oxide film on the surface, which regenerates if it is scratched. We must have virtually zero carbon concentration because of the problem of carbides forming, chromium carbides forming. We need a low martensite start temperature, but not too low, so that we can exploit the full capacity of the phase transformation. And we need to suppress the martensite start temperature with solutes other than carbon. But at some temperature, it must be capable of being fully austenitic. Now, if you add lots of chromium, then you can end up with some delta ferrite, which remains stable at all temperatures. So we need to balance the alloy so that it can become fully austenitic at high temperatures. And it's important that it solidifies as delta ferrite, because sometimes delta ferrite can absorb impurities, right? And therefore you stop hot cracking of the welding alloy. Whereas if it solidifies as austenite, austenite rejects the impurities into the liquid, and therefore you tend to solidify the liquid at too low a temperature, and you get hot cracking developing as the weld pool cools. So we designed these alloys here. This has a very low carbon concentration, chromium 12%, 4% nickel, so to ensure that it becomes austenitic at high temperatures, and otherwise very, very simple. Now, this is a composition specification, really, that is for martensitic stainless steels, right? But we don't want a very large carbon concentration. So you can see that the transformation happens at a low temperature, okay? Both of these alloys transform at a low temperature, which is exactly what we want. But these are stainless steels. And residual stress has two effects. One is that you have a locked-in stress system, which reduces your design parameters. But the second is that you can get ugly distortion of your welded component. So here, for example, you can see that these plates, which were originally lying flat on the surface, after welding, they've developed a distortion with an angle between these two. And if you use a welding material which remains fully austenitic up to room temperature, then you get a large distortion. By using this low temperature transforming alloy, you dramatically reduce the distortion and therefore also the residual stresses if this component was large. So I'll finish the lecture there. And what this shows is, it is so incredibly possible to control a whole bank of features of phase transformations to achieve a good combination of mechanical properties, even when you make large-scale structures. And I'll be happy to answer questions.
Thank you so much, Harry, for your lecture today. We are open to questions if there are. Is there any specific from?
Yes.
Please, Roberto. Yes.
So, good afternoon. Thank you again, Harry, for your very interesting presentation. My question is as regard the austenite grain refining in tube steel. Yeah. When you say grain refinement, are you speaking about the size of subgrain?
Yeah. So I'll share the screen again just to show you. So what I meant was, these regions in which you can get dislocation plasticity, they decrease as the amount of twinning increases. Okay, so effectively that's reducing the regions of austenite, starting with a coarse austenite grain. It's subdivided into smaller and smaller regions as deformation twinning progresses, and that is the dynamic grain refinement by partitioning with twinning.
Okay. And then it's mean a nanometric size.
It can become, the original austenite grain size you can see here is like 50 micrometers, but the twinning subdivides it more and more as deformation proceeds, and that gives us effectively a dynamic hole patch effect. So the size is decreasing and the strength is increasing continuously.
Okay. Yes. Okay.
Okay.
Very good. Thank you.
Yeah. Maybe there is some noise because I'm in the close to the corridor where there are students. But there is maybe another question.
Yeah, Octavio.
Let me check. Yes, Octavio Rafael, please make your question.
Hello, hi again. I have two questions about the soldering alloys that you design. With this new soldering design or alloy, you can avoid the heat treatment after the soldering. That's the first question. And the other is these alloys reach the commercial state already? Thank you.
Yes, you can buy them, for example, from ESAB. We worked with ESAB, but I'm sure you can buy them from several producers now. So the question of heat treatment is really important because sometimes you use heat treatment to eliminate or reduce the residual stresses, but there are components where you cannot do that. So the stainless steel welding material that we designed was intended for submarines. Okay, and for submarines you have a high strength steel to form the body, and then when you weld it, that's it. You don't want to heat treat it at all because the strength of the actual steel will decrease if you do that. So there's no question of heat treating at 500 or 600 degrees centigrade to reduce any residual stresses. So it really depends on what the application is. If you can avoid heat treatment, that's a good thing, and you can buy these electrodes, whether they are for stainless steels or for ferritic steels, to mitigate residual stress.
Thank you very much.
Okay.
Yeah, thank you so much to you. Again, this is the 10th lecture, so we will have one lecture more on Friday, and then we are finished with your lecture. Just to answer to your email, I think Professor Hani will be very pleased to have his lecture on his discharge crucible method, if possible, of course. And I think we will go on in this direction because it is something nice that the students, especially students of mechanical engineering that I do have in my classroom, they can have a look at what's going on with some practical tools to do and to build. And Roberto, you have one more question, maybe, if there is time from Harry?
Yes, no problem.
It may be possible. Okay, thank you. As regards the improvement of hydrogen embrittlement resistance by aluminum in solid solution, there's a minimum to start seeing some beneficial effect in high strength steel.
Yeah, so this is only for the austenitic steel, okay? Because the hydrogen sits in different interstices in ferritic and austenitic steels. And the first principles calculation that I showed you showing an expansion of the whole size is for the austenitic stainless steel.
Okay.
Austenitic drip steels, rather.
Okay. It's very clear. Thank you.
Okay. Okay, so Fabio contacted Professor Hennig and he agreed, and tomorrow it will be online. Yeah.
Okay. Thank you so much, and thank you to all of you. And well, I think that if you have any further question to Francesca, to the other guys that today we had several people from France that I will meet tomorrow, hopefully. Maybe not for work, but for a glass of wine or what? But they will be there traveling from Metz. And what else? Well, I think that all the situation is nice. And thank you again for all the lectures you have been giving to us. And let's do with the last one on Friday. So thank you so much, and have a nice evening. Bye.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Thank you.
Thank you, Francesca.